The Once and Future Present, Episode 16, Ellipses, Orbits, and Revolutions. Welcome back to the Once and Future Present, the AP European History podcast from Hammer History Productions. I'm your host, Casey Brooks, and today we're diving into a fascinating turning point in history, the scientific revolution. This episode is part 1 of our look at Chapter 16 of McKay's A History of Western Society, and we'll focus just on the scientific revolution. Joining me are our regular guests, Dr. Morgan, who helps us understand the political and economic context of these big shifts.
Thanks, Casey. Always excited to talk about how new ideas reshape power structures.
And Professor Theo, our guide to intellectual and social change. Welcome back.
And I'm thrilled to explore how science changed not just what people believed, but how they thought about the world and their place in it.
Great. So, Professor Theo, let's start simple. What exactly was the scientific revolution?
Good question. The scientific revolution was a major transformation in European thought that occurred roughly between the mid-1500s and late 1600s. It marked a shift from relying on ancient authorities and religious doctrine to using observation, experimentation, and mathematical reasoning to understand the natural world.
So before this, people didn't use experiments to figure things out?
Not really. At least not in a systematic way. Most educated Europeans in the Middle Ages based their understanding of the world on ancient thinkers like Aristotle and Ptolemy, as well as on religious teachings. The scientific revolution introduced a new method. We often call it the scientific method, that emphasized empirical evidence, meaning knowledge based on observation and experience, rather than tradition or pure reason alone.
That makes me wonder, what was going on in other parts of the world? Were scientists or mathematicians in places like the Middle East or India doing similar work?
That's a really important point, Casey. While the scientific revolution is usually described as a European event, it wouldn't have happened without earlier developments from other parts of the world. For example, Islamic scholars in the Middle East preserved and expanded upon the works of ancient Greek philosophers like Aristotle and Ptolemy. They made advances in astronomy, optics, and medicine long before similar changes occurred in Europe.
And let's not forget mathematics. The number system we use today, the Hindu-Arabic numeral system, was developed by Indian mathematicians and passed to Europe through the Islamic world, especially through Spain. This positional base 10 system, which includes the concept of zero, replaced the cumbersome Roman numerals and made calculations much easier.
The Islamic Empire played a crucial role in transmitting that knowledge. Cities like Cordoba and Toledo in Muslim-controlled Spain were major centers of learning. During the Reconquista, the Christian reconquest of Spain, many of those texts were translated into Latin. That's how a lot of this scientific and mathematical knowledge entered Europe and laid the groundwork for future discoveries.
You mentioned Ptolemy. I remember hearing that name in middle school, something to do with the planets.
Exactly. Ptolemy was a Greco-Roman astronomer who developed a model of the universe where Earth sat at the center and everything else, the sun, the planets, the stars, moved in perfect circles around it. We call this a geocentric model.
So Earth in the middle, got it.
Right? And this view wasn't just scientific, it was theological. The Church supported the geocentric model because it aligned with biblical interpretations about humanity's central place in creation.
But then along came Copernicus.
I've heard of him. Didn't he say the sun was in the middle?
He did. In 1543, Copernicus published On the Revolutions of the Heavenly Spheres, proposing a heliocentric model, from the Greek for sun-centered. According to his theory, the Earth and the other planets revolved around the sun.
That sounds really basic today, but I bet it was super controversial back then.
Extremely. Copernicus waited until the end of his life to publish, likely because he knew it would provoke backlash. His model challenged not only scientific ideas, but also religious doctrine and the social order that depended on them. It's also important to remember that this was all happening during the Protestant Reformation, when the Catholic Church was already under enormous pressure. Reformers like Martin Luther were challenging church authority and its interpretation of Scripture. So when Copernicus and later Galileo put forward ideas that seemed to contradict the Bible, the Church saw them not just as scientific proposals, but as part of a broader threat to its dominance in Western Europe. In a time when religious unity was already fracturing, any challenge to church teachings, especially one that suggested the church had been wrong about the structure of the cosmos, was treated very seriously.
So, did everyone accept it right away?
Not at all. It took decades. Later scientists, like Johannes Kepler, improved Copernicus' ideas by showing that planets move in elliptical orbits, not perfect circles. That was huge because it fit better with actual observations.
Elliptical means oval-shaped, right?
Correct. Kepler used mathematical laws to explain planetary motion, making the heliocentric model more convincing.
And don't forget Galileo Galilei. He used a telescope, a relatively new invention, to observe the moon's surface, Jupiter's moons, and sunspots. These observations directly contradicted the old belief that the heavens were perfect and unchanging.
Wow, that must have made people nervous.
Very much so. Galileo wrote in Italian instead of Latin to reach a broader audience, which made his ideas more dangerous to church authorities. In 1633, the Inquisition forced him to recant or publicly withdraw his support for the heliocentric model.
What's the Inquisition?
A powerful institution within the Catholic Church that aimed to root out heresy. If your ideas challenged church teachings, you could be tried and punished.
Yikes. So what happened to Galileo?
He was placed under house arrest for the rest of his life. But his work had already changed how people thought about science.
And it didn't help Galileo's case that he had previously enjoyed the support of Pope Urban VIII. In fact, the Pope had been a patron of Galileo's work.
Wait, that doesn't sound like a problem. Wouldn't that help Galileo?
Yes, until in one of his writings, Galileo included a character named Simplicio, meant to represent someone who argued against heliocentrism, who echoed Urban's own views. Many took this as a personal insult to the Pope. What might have been an academic debate turned into a political and personal conflict.
Ooh.
That's an important nuance. While Galileo faced harsh treatment, it would be wrong to say the Catholic Church was wholly anti-science. Many Jesuit scholars were deeply involved in scientific research, including astronomy. The Church supported calendar reforms and even sponsored observatories. But it was deeply concerned with maintaining its social and cultural authority, especially as its political dominance was being challenged by Protestant reformers. The trial of Galileo was about power as much as it was about planetary motion.
That sounds messy and complicated.
History often is.
So, where does Isaac Newton fit into all of this?
Newton. He stands at the peak of the scientific revolution. In 1687, he published the Principia Mathematica, which combined the work of Copernicus, Kepler, and Galileo. Newton formulated the law of universal gravitation, showing that the same force pulling apples to the ground also kept the moon in orbit around Earth. But that wasn't all. He also made major contributions to our understanding of light and color. Using a prism, Newton demonstrated that white light is actually made up of many colors, which we see as the visible spectrum. This was revolutionary because it challenged the old idea that color was simply a mixture of light and darkness. Newton showed that color is a property of light itself, not a distortion or impurity. This work laid the foundation for the field of optics. Newton was also one of the two independent inventors of calculus, a powerful mathematical tool used to understand motion, change, and forces. The other was the German philosopher and mathematician Gottfried Wilhelm Leibniz. Both developed similar systems around the same time, leading to a heated dispute over who should get credit. This controversy highlighted the growing importance of publishing your findings quickly in the scientific world. Sharing your work in journals or books wasn't just about communication. It was about establishing priority and recognition for discoveries.
That's so cool. So he basically proved that the universe follows predictable rules?
Exactly. Newton believed the universe was like a giant machine operating according to natural laws that could be discovered through reason and mathematics.
This reminds me of the Enlightenment. Is there a connection?
Absolutely. The Enlightenment grew directly out of the scientific revolution. If nature could be understood through reason and evidence, why not human society, politics, or religion? The success of science gave Enlightenment thinkers confidence in the power of rational thought.
I see. So what were the key methods scientists used during the revolution?
Two major approaches: empiricism and rationalism. Empiricism, championed by thinkers like Francis Bacon, emphasized observation and experimentation. Rationalism, associated with René Descartes, stressed the use of logic and mathematical reasoning.
So Bacon said, test it out, and Descartes has said, think it through?
Exactly. Descartes is famous for the phrase cogito, ergo sum. I think, therefore I am. He doubted everything except his own ability to think, and from there built a whole system of knowledge.
That makes me wonder, what's the difference between deductive and inductive reasoning? I always get those confused.
Great question. Deductive reasoning starts with a general principle or theory and works down to a specific conclusion. Think of it like math. If all men are mortal and Socrates is a man, then Socrates is mortal. That's deductive. Inductive reasoning, on the other hand, starts with specific observations and builds up to a general conclusion. Like if you see the sun rise every morning, you might conclude it will rise again tomorrow. That's how a lot of scientific discoveries were made, through repeated observations and experimentation that led to broader theories.
But these two methods weren't enemies. Over time, they blended into the modern scientific method. Ask a question, form a hypothesis, experiment, and analyze the results.
Makes sense. Were there institutions that helped spread these ideas?
Yes, scientific societies played a big role. For example, the Royal Society in England and the French Academy of Sciences brought scientists together to share discoveries and conduct experiments. Publishing journals also helped spread ideas across Europe.
And we shouldn't overlook the printing press, which had already revolutionized communication. It made it possible to share new scientific findings widely and quickly.
Were women involved in the scientific revolution?
That's a great question. Women were largely excluded from formal institutions, but some still contributed. For example, Margaret Cavendish wrote philosophical works about science, and Maria Winkelmann, a German astronomer, discovered a comet. Sadly, her work was often credited to her husband.
That's frustrating.
It was. The scientific revolution didn't challenge gender roles as much as you might hope. In fact, some new scientific theories were used to reinforce traditional views of women as inferior.
So not all progress is progress for everyone. I also read about something called alchemy. Was that part of science too?
Alchemy was a kind of early chemistry that involved trying to transform base metals into gold or discover the elixir of life. At the time, many thinkers didn't view alchemy as irrational or unscientific. In fact, some of the most respected scientists of the age were deeply involved in alchemical research, including Isaac Newton himself. Newton devoted considerable time and energy to alchemical texts and experiments, believing they held secrets about the fundamental structure of matter and the universe. It might sound like fantasy today, but alchemy played a real role in the development of modern chemistry.
Were there changes in other fields too, like medicine?
Absolutely. The scientific revolution wasn't limited to astronomy or physics. It also transformed how people understood the human body. For centuries, most European medical knowledge came from Galen, a Greek physician whose work was based more on theory than dissection. He believed in balancing the four humors, blood, phlegm, black bile, and yellow bile, to maintain health.
Wait, is that why in old books or movies, doctors are always bleeding people or using leeches?
Exactly. The idea was that illness came from an imbalance of the humors, so treatments like bloodletting were meant to restore that balance. It sounds strange now, but at the time it was considered advanced medicine.
But in the 16th century, people like Andreas Vesalius began to challenge that. He conducted detailed dissections of human cadavers and published on the structure of the human body in 1543. It was a breakthrough because it corrected many of Galen's anatomical errors, which had been based on animal dissections.
And later scientists like William Harvey used experiments to demonstrate how blood circulates through the body, showing that the heart functions like a pump. This marked a shift toward understanding the body as a system governed by physical laws, not mystical forces. People doing alchemical experiments learned a lot about substances and reactions.
Did the tools scientists used change too? It sounds like they were able to see and measure things in new ways.
Absolutely. One of the key drivers of the scientific revolution was the development of new scientific instruments. The telescope, which Galileo used to study the moon and planets, allowed astronomers to gather data that had never been visible before. Around the same time, the microscope opened up a whole new world by revealing the structure of tiny organisms and biological tissues.
And don't forget instruments like the barometer, which measured atmospheric pressure, and the air pump, which allowed for experiments on vacuums and gases. These tools didn't just confirm existing theories, they made it possible to ask entirely new questions. Scientists began to trust what they could see and measure, rather than relying only on ancient texts or philosophical speculation.
Instruments became essential to scientific credibility. If you wanted to be taken seriously, you needed to base your arguments on what your instruments showed you. This shift helped reinforce the experimental nature of the new scientific method.
Were those kinds of discoveries only happening in astronomy and medicine, or were there other areas of science that were changing too?
Another great question. The scientific revolution also sparked big changes in fields like botany and natural history. European explorers brought back plants, animals, and minerals from around the world, and scientists began to systematically study and categorize them. This led to the beginnings of taxonomy, the classification of living things, which would later be developed further by figures like Carl Linnaeus.
These efforts weren't just scientific, they were also connected to empire and trade. Colonization created a surge in curiosity and necessity to understand and exploit new resources. Cataloging nature became part of managing empire, but it also opened up new ways of thinking about the natural world.
And many scientists during this period didn't call themselves scientists. They referred to themselves as natural philosophers. They believed that by studying God's creation, they could come to better understand God. This idea helped make scientific inquiry more acceptable in religious contexts. Over time, some thinkers developed deism, the belief that God created the universe but doesn't interfere with it, much like a clockmaker who builds a machine and lets it run. This mechanical view of the universe aligned well with the discoveries of Newton and others. Many Enlightenment thinkers began to see the entire universe as a vast, orderly machine governed by natural laws that could be discovered, measured, and understood. This idea, the mechanical universe, suggested that everything from the motion of planets to the workings of the human body operated like clockwork, with predictable causes and effects. It was a dramatic shift away from viewing nature as mysterious, unknowable, or driven by divine will in every moment. Instead, the world became something humans could map, explain, and potentially master through reason and science.
Astrology also played a role. Many early scientists, including Kepler and Galileo, practiced astrology. The lines between science and magic weren't as clear as they are today.
That's wild. So the scientific revolution wasn't just about clean-cut science. It was messy, experimental, and sometimes mixed up with superstition.
Precisely. It was a time of transition. People were rethinking the universe, the body, knowledge itself, but they still carried old beliefs alongside new ones.
How did the church react to all this?
The Catholic Church, especially during the Counter-Reformation, was cautious and often hostile, but not uniformly so. Some clergy supported scientific research, especially when it could help with calendar reform or astronomy. Protestant countries tended to be more open to new ideas, partly because they lacked a centralized religious authority like the Pope.
Did the scientific revolution only happen in Europe?
Mostly, yes, though Europeans built on knowledge from other cultures. For example, Muslim scholars preserved and advanced ancient Greek works, and Chinese inventions like the compass and printing press had long influenced Europe. But the scientific revolution, as a distinct intellectual movement, took place primarily in Western Europe.
This is all so fascinating. It sounds like people began to believe that knowledge could grow and improve over time.
Exactly. That's a key legacy of the scientific revolution. It laid the foundation for modern science and the belief in progress, the idea that the world can be understood and improved through human effort.
Well, that brings us to the end of today's episode. Thanks to Dr. Morgan and Professor Theo for helping us understand how the scientific revolution turned the world upside down. Or maybe we should say heliocentrically right side up. And for all of you listening, don't forget that Hammer History Productions has music albums available on Spotify, YouTube Music, iTunes, and most other streaming services. Check them out if you want to review AP Euro or AP US with a beat. Stay curious, think critically.